So I break it into two parts, part A and part B. So today, let's go over part A. We're going to talk about area in polar coordinate. First, let's think about if we have a sector of this big circle, so like this sector, like a sector of this, like this big pizza over here. And this circle has radius r, and the center angle here to be theta, and that is measured in radian. What is the arc length opposite to this center angle? Well, if the data is 2 pi, then this arc length will be 2 pi r. It's the whole circumference of the circle. If the data is pi, that will be pi r. That will be half a circle. And in general, this arc length here is going to be the radius times the center angle here, where this is in radian. So it's r theta. Okay, so the arc length here will be r theta. What about the area of this sector? Can someone make a guess? Make a reasonable guess? What will be the area of this sector? What do you think? Now, to divide the formula formally, let's think about this way. What's the area for this whole circle? It is what? Pi r squared. Well, you guys can actually hit the space bar to speak, okay? Even when you're muted, you hit the space bar, then you're able to speak, okay? So pi r squared, okay? So that's the area for the whole circle. Now, this whole circle corresponds to the center angle. What's the center angle correspond to the circle? That will be what? 2 pi, right? The center angle will be 2 pi. Okay, so that will be 2 pi. Okay. Now, this angle is, you see that this area is actually proportional to this center angle. The bigger this center angle, the bigger the area. So we will use this center angle, divide by this 2 pi to find out the ratio between this sector to this whole circle. So we'll use theta divided by 2 pi times the total area. That will give us the area of this sector here. Now, as you can see, the pi here is going to divide out, giving you 1/2 r square theta. Okay, so the area of a sector that is part of a circle with radius r and with center angle to be theta is 1/2 r squared theta. Another way to think about and easy to remember is, think about that this is almost like a triangle. Think about like a triangle. We know how to find the area of a triangle. It is 1/2 base times height. The base over here, you can think about as this arc length over here, which is r theta. And the height, think about it as this radius, so times r. Then you will also, you get this result. It's 1/2 r squared times theta. Okay, so that's the area of a sector of a circle. Now, what about the area bounded by a polar curve? This polar curve over here, between theta equal to A to theta equal to B. So think about this area over here, the blue area over here. As the data increase from A to B, then this ray from the pole to this polar curve, this ray over here, is going to sweep out this region. So imagine that this one over here turn and turn, finally stop here. And that ray is going to sweep out this whole region here. The area for this region is going to be the integral. Okay, well, what do you think? What should I put there? Anyone?
1.5.
It's 1/2. Yes, 1/2. Got it. So it is 1/2. 1/2 what?
F of theta squared.
Yes, very good. So it is f theta and then square, right? And then here, d theta. Okay. So another way to write this here is, well, as you sweep out, you see this R over here, right? So R here is going to change as the data change from A to B. This R here is going to change. So sometimes R here, sometimes here, okay, sometimes there. Okay. Now, if you divide this into small sector, then each sector is kind of like part of a circle. Okay, it's a sector of a circle. Each one is going to be 1/2 r squared. Okay, and then times the center angle of that sector. So that's a small change in data. So d theta. So think about this is like the area of a sector. Okay, a sector here. When d theta here is very small, and then you sum them up. Okay, use integral. Then you integrate this. You will get the area of this whole. You get this total area that is going to be bounded by this polar curve and this ray data equal to A and this ray data equal to B. So data here change from A to B. So we add this up, B. So these two are actually they mean the same thing. Okay. So R is F data. Okay. So 1/2. Okay. Think about this one here. 1/2 R squared d data. Okay. And then you integrate data go from A to B. You get this total area over here. Now, because R is equal to F data, so you can also put F data over here instead of R. These two mean the same thing. Okay, so that's the formula. Now let's look at some example. The first example, we try to determine the area of this, of the inner loop of this. Well, we learned from the previous section. The graph of this is a lemon soil, right? It's a lemon soil, like a snail, okay, in French. So here's a graph of this function. It's right here. Okay? Here is the inner loop of this polar curve over here. Now we try to find the area of this inner loop, which is the green, highlight the area over here. Okay. We will need to first, well, we will use this formula, right? We use this formula, but we need to find out A and B, or alpha and beta. Okay. So we need to figure out data go from what to what when we go from here to here. Okay. When we trace out the inner loop. Okay. So how do we do that? We need to know the value of data where the curve go through this origin, right? So when does it go through? I put it over here. Okay. But how do you find out? How do you know? How do you know when data equal 2 power over 3 and 4 power over 3? Then the loop is going to go through this pole. Go through this pole over here. How do we know? How can we find out these two data, these two angles? Okay. Now we can get these two angles, okay, by setting what equal to 0. At the pole, what do you observe? What equal to 0?
R.
R equal to 0. Yes, you got it. So the pole R is equal to 0, okay? So the radius, actually the R equal to 0, then the curve will go through the origin, okay? Actually, here we should say the pole, okay? So the curve will go through the pole if and only if R equal to 0. When R equal to 0, right? When R equal to 0, then you will have then the curve will go through the pole, okay? So if you want to find where the curve goes through the pole, then you will set R equal to 0. So we're going to set R equal to 0 here in this equation. So we get 0 equal to 2 plus 4 cosine theta. Now, solving this, cosine theta equal to what? Is it negative 1/2? No, it's negative 1/2, right? Cosine theta equal negative 1/2. And because it make one round, we finish one period, when data go from 0 to 2 pi. So let's think about the solution for this trig equation when data go from 0 to 2 pi. So when data go from 0 to 2 pi, okay, 0 to 2 pi, what does data equal to? You see over here, I actually graph this in Cartesian coordinate, okay? R equal to 2 plus 4 cosine theta, okay? This is data, this is for the R. And you see that intersect here and here when data go from 0 to 2 pi. 2 pi is about 6.28, okay? So from 0 to 2 pi, intersect here and here. What would this angle here? What would this angle here? Oh, wait, negative 1/2. Yeah, so the equation, so to solve this equation right here, one way to do it is you can actually graph it in Cartesian coordinate, right? And you find the intersection point right here, okay? So this is called solve by graphing. So what would this angle here be? Cosine of what equal to negative 1/2? Looks like is what? This one here is 2 pi over 3, okay? So let's see. So that's 2 pi over 3. And what about the other angle?
4
4
pi.
pi over 3. Yes, you got it, okay? So this two angle will be from 0 to 2 pi that make this equation, make 0 equal to R plus 4 cosine theta equal to 0, okay? Make R equal to 0. So we got theta equal to this two number, okay? Now we found that when theta equal to 2 pi over 3 and 4 pi over 3 is going to pass this origin. So it's like this. So when 2 pi over 3 is here, and then it go around, and then when you get to 4 pi over 3, you end it back here. So when data go from this to this number, you finish the inner loop. Okay, we go finish the inner loop. Okay, so you can see why we need to use why we need to find the value of data where the curve goes through the origin, right? This 2 point, okay, define where the inner loop start. Okay, so inner loop start when data equal to 2 pi over 3, and then it ends when data equal to 4 pi over 3. We need this two number. Okay, we need this two data value. Once you know this two data value, we can find the area, right? So what was the formula for area? The formula for area is this one, right? Okay, so for area, so you can have this, okay? So we know the data go from, we just found that it is what? 2 pi over 3, sorry, it's going to be 2 pi over 3 to 4 pi over 3, okay? So the D data here, data go from 2 pi over 3 to 4 pi over 3. What should I put inside? According to the formula. According to this formula, What should I put inside here? 1/2, right? 1/2 what? 1/2. What is the R?
2 plus 4 cosine. Theta.
Yeah. So we have R. R is 2 plus 4 cosine theta. Okay, and then we're going to put it over here, right? So 2 plus 4 cosine theta. 2 plus 4 cosine theta. Okay, and then we're going to square this. Okay, square that. So this is 1/2 R squared d theta. So we're using this formula. And theta go from this to this. Now, how do you evaluate this integral? We had to use the perfect square formula, right? The perfect square formula is stated here. So use the perfect square formula to expand this. What do we get? Anyone? Leah?
Yes, it's 2 squared plus 2, and then 2 multiple 2 and then 4 cosine theta, and plus
Plus this
4
one's
cosine theta squared.
Yeah, you got it. Good job. Okay. So it's going to be this, right? Use the perfect square formula. Now, after this, then we'll have, then simplify this, we get 4 plus, this is 16 cosine theta, and this is 16 cosine square theta. And then the 1/2 in front here are going to divide out with 4, 16, and 16, giving you this expression over here. And you're still integrating from 2 pi over 3 to 4 pi over 3. Okay. Now, how did you get from here to here? Looking at this function, this is cosine square. Whenever you integrate sine square theta or cosine square theta, you think about the half angle formula. When this exponent here is even, well, can someone tell me what does cosine square theta equal to in half angle formula? What is it equal to? Cosine square theta equal to? I guess some of you might forgot, right? So might forget. So let me remind you. The half angle formula says that it is cosine square theta is 1/2 of 1 plus cosine 2 theta. Okay, let me put it on the side here. Okay, so remember before we talk about integrating function of this form, when you have sine x cosine x, one of the vector here raised to m and m power over here. And if both of them are even, then we use a half angle formula to find the integral. And the half angle formula is this. Cosine square x is 1/2 of 1 plus cosine 2x. And sine square x is 1/2 of 1 minus cosine 2x. So those are the two formulas that you use a lot when you use polar coordinate and when you do the integration. When you have the exponent on cosine and sine are even, then you use a half angle formula. So use a half angle formula over here. Cosine square theta is 1/2 of this. Multiply this by 8. 1/2 times 8 give you 4. So that's how you got this one here. So it's 4 times 1 plus cosine 2 theta. So remember the half angle formula whenever you encounter sine square and cosine square. Okay, integrating. Now we just need to combine item. 2 plus 4 is 6. Okay, and now we can just find antiderivative this term by term. Okay, now everybody tell me what's antiderivative 6 with respect to theta? What's the antiderivative this? The whole function right here? 6? 6 what?
Theta.
6 theta, okay. And plus 8, what's antiderivative this?
Sine theta.
sun data. And what's the antiderivative of this?
2 sine 2 theta.
2 sine 2 theta. You got it. Good job. Okay. So the antiderivative of this, right? Antiderivative of this is going to be sine of 2 theta. But then when you integrate, you divide by the coefficient of this theta. So divide by 2. Then 4 over 2 give you 2. So that's why you have the 2 over here. So you get 2 sine 2 theta. That's the antiderivative of this. Okay. Now substituting the upper and lower limit, you got the result. Okay. When you do homework, when they ask you for exact answer, which one is the exact answer here? The exact answer is the one here with this radical. That's the exact answer here. Okay, this should be the exact. This one over here is the decimal approximation. Okay, because the digit here actually continue forever. So this is not exact. Okay, so this is approximation. So be careful when you do assignment that they ask for exact or they ask for approximation. Okay, now I hope that you're able to follow the work we've done in this integral. And if you run into trouble, maybe section 7.2 is the one that you might want to go back to review, how to find antiderivative of function of a trig, how to find antiderivative of trig integral, trig function. So basically, I think this is a formula that you use a lot, half angle formulas. Okay. Now the next situation will be like this. Before was we only have one curve, right? The region only from here to here. Now what about you try to find the area that is enclosed by two polar curves, one here and one here. This is the outer curve. This is the inner curve. We're trying to find the region bounded by this two polar curve and this way and this way. Data go from alpha to beta. Well, would that be just the outer radius? No, would that be just the area, this area over here, subtracting this area here, or the inside, right? Okay, so it makes sense that we come up with this formula. So what would this formula, what do you think I should put as a formula for the area of this region? It is what?
1/2.
1/2.
And
You got it?
G theta minus F theta squared.
1/2.
I think.
Yes. So remember before was R square, right? So we take the outer R and then we're going to square that. Okay. Now, if I have this integral, that will correspond to the area of this, the outside curve enclosed by the outside curve and this two rate. And then, but we have to subtract the area of enclosed by this inner curve. So I'm going to subtract. So subtracting this area by the enclosed by the inner curve. So this will be the formula for the area enclosed by this two curve. And data go from alpha to beta. So okay, so it makes sense to get that. And so that's another formula that maybe you can try to understand and then remember. Now let's try to determine the area lie inside this curve and outside this curve. Okay, now I draw the graph right here. So this curve here is a lemon saw, right? Okay, is this one, the blue one right here. And then I=2 is a radius. It's a circle with radius equal 2. It's the red one right here. Okay. So inside the blue, outside the red, then there has to be this green. Highlight the area over here. Now to determine this area, we first need to find the intersection here and here, right? So we want to find out what data correspond to this point and this point. How do you find the data at this and this? Can someone tell me? How do you find this data at this intersection? And
R1 equal to R2.
so you did say that let this two equal, right? So yes. So we solve this two polar equation together, right? You're going to set this equal to this. So when we set this equal to this, you will have what? 2 equal to 3 plus 2 sine theta, right? So we're going to solve the equation 2 equal to 3 plus 2 sine theta. Okay, we set this to equal. And then we get sine theta is -1/2. Okay, on 0 to 2 pi, what are those angles? Sine theta equal -1/2. What does theta equal to? Anyone? Okay, yeah? You want to say something? Okay, one way to do that, I heard someone trying to say something. Can you speak up? 7 pi over 6. Okay, you got it. And what's the other one?
11 pi over 6.
Yeah, you got it. Okay, 7 pi and 11 pi over 6. Okay. The way that you find this, for me, I will do it this way. Let's just find it at the first quadrant, right? So sine theta is equal to 1/2. Let's think about it at the first quadrant, 0 to pi over 2. Then theta is equal to pi over 6. So this pi over 6 is a reference angle. So when we try to find those angles, we need to use the reference angle. So we know sine is going to be opposite over hypotenuse, okay, which is y over r, right? Sine is y over r. Y is positive here and here, and negative here and here. So sine will be positive over at this 2 and negative at this 2 quadrant when the angle are at this 2 quadrant. So this is negative. So therefore, you go to this 2 quadrant, and then you're going to draw this reference angle pi over 6. So this is pi over 6, and then you draw this reference angle pi over 6. Okay, then you can just read from this diagram. So what will be this angle right here? That is 7 pi over 6. And what's this angle over here? That is 11 pi over 6. And that's how you find it. So you first find that angle at the first quadrant and use it as a reference. And then you look at the side and determine if either at above over here or below over here. And then you use the reference angle here and here. And then you can read from the diagram to see the angle here and here. Okay. Okay. So we got 7 pi over 6 and 11 pi over 6. Now we're trying to find the region enclosed by 2 curves, right? So should I go from 7 pi over 6 to 11 pi over 6? Should I integrate from this to this? If I integrate from 7 pi over 6 to 11 pi over 6, I actually get the region that's bounded between this curve and this curve, bounded by this ray and this ray, right? So only this is going to be between these two right here, okay? But we're looking for this. We're looking for this above. So you need to think about an angle is going to be smaller than this, okay? Smaller than this, okay? And equivalent to 11 pi over 6. So you're going to subtract 2 pi, okay? Subtract 2 pi from this. So that will be negative pi over 6. So another way to think about this angle here, this is actually negative pi over 6, okay? So it's negative pi over 6 over here. This is negative pi over 6. So we're going to take this one and this one. Negative pi over 6 to this. Because that way, when data increase from negative power 6 and then go all the way to 7 power 6, then we get this region, right? We get this region that is going to go from this to this. So do not take the 11 power 6, okay? You take this. So think about what will be the lower and upper data that you integrate. So that's why this integral here, it go from negative power 6 to 7 pi over 6. Then you're going to sweep out this region right here. Okay, now after this, we're going to use the formula, right? 1/2 the outer radius squared. The outer radius is 3 plus 2 sine theta. So this is the outer R, okay? The inner R, what's the inner R? What's R? Inner R?
2.
Yeah. So it's 2, right? Okay, cool. So that's 2. So use that formula. So 1/2 R, outer R square minus inner R square, and then d data, right? Data go from this to this, from small to big, because that corresponds to that region. And then you use the perfect square formula to expand this, and then combine items. And then over here again, we encounter this sine squared data. Then we use a half angle formula, right? Okay, now everybody can tell me sine squared data equal to what? For half angle formula. 1/2, 1 minus cosine 2 data, right? So we're going to use that to replace this. Now, after that, you will simplify, okay? And you got that. Now we just need to find anti-duality here, okay? So what's the anti-duality of this? Let's just practice. What's anti-duality of, right? We can take the 1/2 outside because that's a constant multiple, right? Okay, and now we can take the anti-duality of this turn by turn, right? So that will be what? 7, everyone?
Data.
7 data, okay, good. And then minus, okay? Anti-duality, this is minus 12, what? Cosine data. Yes, good. And then this will be what? Minus, what's anti-duality? Minus sine 2 data, right? Okay. So find anti-duality, you got that. And you substitute upper and lower limit, and you find the result. Okay, this is the exact answer here, and this is the decimal approximation. Okay, all right. Am I going too fast for you guys, or is it just okay? Give me a thumbs up if you are here. All right, let me see the
It's okay.
participants. Huh?
It's okay.
Okay. It's okay? Okay, good. Okay. Okay, let's look at this next example. We're going to determine the area is out. Okay, it's like sometimes outside this, inside this. Okay, this time it's going to be outside of the blue, inside of the red. So outside the blue, inside red will be this one over here, kind of like a mustache. Okay, so for that one over here, we've already found the data, right? Here and here. So to find this area, we're going to use from what? From this, right? To the bigger one, which is 11 pi over 6. Okay, so we're going to use that. Okay, so that's why we got this to this, the data. Okay, 1/2. Okay, looks like this region is the outer R will be the red one right here, right? The inner will be the blue one, right? So the outer R will be what? Will be 2, right? R will be 2. Okay. And the inner will be what?
3 plus 2 sine theta.
Yes. So that will be 3 plus 2 sine theta. And then after you simplify, okay, use the perfect square formula to expand this and combine item. You got this one over here. Again, you see again and again, you went into sine square theta or cosine square theta, right? So here you use what angle formula? Half angle formula, right? So use half angle formula for that one. So that's why again and again use half angle formula. Sine square theta is 1/2 1 minus cosine 2 theta. Okay, and after that, simplify. You got this expression. Now let's find antiderivative. So we can take this 1/2 outside. Okay, so this 1/2 we bring in front. So you got this. Okay, and then we find antiderivative here. Let's find the antiderivative for everyone. So what do we get for this? That is -7 theta, right? -7 theta, and this is positive cosine theta, and antiderivative this is sine 2 theta. And then evaluating, the answer is about 2.196. Okay. Notice that for this area, the outer and inner function were opposite, right? They switch, okay, from the last example. Okay. So you have to be careful. Sometimes it's outside of which, inside of which. You had to make sure you got it right. Otherwise, you get a different area. Okay. Okay. Now let's look at the next example. We still have the same curve. Notice all this example. We still have the two curves are the same, but this time it's going to be inside both. So what do you mean inside both? So inside the blue and also inside the red. So that will look like this highlighted area here, right? Now to do that, well, if you find this data, right? So if you see, do you see here? So when data equal to this and data equal to this, okay, you see this ray and this ray, but we still have this region that's between the two rays. So I cannot set up a single integral to represent this green highlighted area, because looks like this is actually has two parts, right? So if data go from say -6 to 7/6, you can get this part right here. But then this part over here, this part here down here like a mustache right here, actually data go from 7/6 to 11/6. So this whole highlighted area cannot be represented. Just use one single integral. So there are two different ways to find this area over here. And use some result that we have calculated before. Okay. So one way to do that is you can find the area of this circle, this whole circle right here. And then you can subtract this white area over here. So the circle, subtract this white area here, is this green area over here. And the white area over here, we already got from example 3, which is this. And what's the area of this red circle? If you guys participate, it's going to be 4 pi. Yes, that is pi times 2 squared, right? Because the radius is 2. Okay, so it's going to be 4 pi. Okay, so that looks a little bit simpler, right? So just use the whole circle area, subtract this white area to get this. Okay, another solution you can think about here is, what's another solution? For example 2, we got this area, this white area here above, right? So we can actually find the area of this lemon soil, right? This blue one, enclosed by the blue, by the lemon soil. Okay, subtracting the white area over here, then we get this green area over here. Okay, so take the area inside the blue curve, subtract the area here, the white part here, you get this green area over here. Okay, so, but how do we find the area enclosed by this blue curve? That's the lemon soil, right? And the equation for that is, what's the equation for that? Is, oh, it's right there. It's already there. This is the equation right there. Right? So how do you find the total area? So how do you find this area over here? The area over here is equal to what? Well, we will integrate the function, which is 3 plus 2 sine theta. Okay, and then, well, the area is what? 1/2, right? So it's going to be 1/2. This R, okay, this one here is the R. R is given by this, remember? This is the R, right? And then the R is changing for that lemon stick, right? R is this is the R, okay? And then you square this, and then you put d theta, okay? We'll change a different color, d theta, right? Now, to finish this lemon soil, theta go from 0 to 2 pi. Okay, so for one lemon soil right here, the data will start from, you can start the data from 0 and then end at 2 pi. They will chase out this whole lemon soil. So data over here will go from 0 to 2 pi. All right, so you got that?
I have a question.
Sure. Yeah, go ahead.
The domain of data is from 0 to 2 pi, right? And why the data is negative pi over 6?
Oh, it's negative pi over 6?
Yes, because
the data is negative pi over 6?
Yeah, because your domain is from 0 to 2 pi, but why there's a negative?
You kind of worry that what happened when data equals negative pi over 6? Actually, they happened here before. It actually okay. Okay, from negative pi over 6 to pi over 6. You see this one over here. You can try it. So if it's negative pi over 6 to that, the domain for data is not necessarily from 0 to 2 pi. Okay, so okay, go back to this problem over here. That's a good question. So data go from 0 to 2 pi, but however, I think if you integrate from say negative 2 pi to 0, you should get the same result. Okay, so as long as you trace out if you trace out this whole lemon soil once, so not necessarily from 0 to 2 pi, you can actually go from negative 2 pi to 0 in that integral. Okay, you can try to do that at home, and I think the result should be the same. Okay. From negative 2 pi to 0, it also traces out the whole lemon soil. So try to get this integral, but we place the upper and lower limit this way, from negative 2 pi to 0. You also get the whole lemon soil. So the negative side here is okay. So if you go, at this one here, go from negative pi over 6 to, so for example, if you integrate this curve, integrate this function, polar function, from negative pi over 6 to pi over 6, if it's 1/2 r squared d theta, but instead of from 0 to 2 pi, it go from negative pi over 6 to 7 pi over 6. what happened here is you actually get the region that is between these two rays, but inside the lemon soil will be this one right here. So it's okay to have a negative. Yeah, it's okay to have negative. Okay, it's a good question. Okay, now we found the area for this whole lemon soil is correspond to this integral. Then we just need to use the result of this integral, subtracting, well, what do we subtract? Subtracting the y part right here. The y part we already calculate, right? In the, I think in the first example, or example 2. Okay, example 2. So the y part we already calculate. In example 2, we got this. So you see what happens this. Okay, let me actually highlight this. Let me put this down there. Okay, so this corresponds to the area of this inside this lemon soil. Okay, so that is this part over here, the integral over here correspond to this, which is this one over here. Okay, and then this one over here. So what is that one over there? That is this one over here is the one that from example 2. Sorry, I had to jump around. Example 2. That's example 2. Oh, it's right here. Okay. Example 2. This one. Okay. Example 2. So which is this one over here. That's the one over here. So when we take this whole area, subtracting this area, subtracting this y part over here, we'll get the result here. So that's this. When you evaluate this integral, again, you use a half angle formula. Okay. So again, when you encounter sine squared data, use half angle formula. Okay. All right. Well, it looks like the second approach is a little bit longer than the first approach, right? But sometimes if you have no other choice, and sometimes you have to take the longer approach. Okay. Okay, the last one here will be homework help. Well, do you have, let me, instead of going so fast, do you guys have question about this? No? Okay. Let me check the chat. Okay. Right, let's do this one. This is one of the homework problem, okay? So we are trying to find the area of the shaded region, which is the blue region over here. Looks like is this lemon soil, take away this flower, like this rose over here. Okay. So let's write down this shaded region. It is outside of this rose and inside of this lemon soil, right? The lemon soil right there. Let me color code this. So the outside one, this time I use the green, okay, right there. And that's is this one. Okay. This is this one right there. And then the inside is this one, which is this one over here. That's the outside, that's inside. Okay, Ri equal to sine of 2 theta, which is a rose. This is the inner polar curve, and this is the outer polar curve. And we're looking for the region is outside of this, but inside of this, the blue region. So R0 here, the outer is 4 plus 3 cosine theta, which is the lemon soil. Now, in order to find this highlighted area over here, we need to use once we figure the outer and the inner, okay, we can use the formula, but then we need to figure out the data. What will be the data in order to calculate this area? We know that the curve is going to complete one round as data go from 0 to what? What do you think? data go from what to what, then the limit star is going to complete one round. And the rows here complete one round.
0 to 2 pi.
0 to 2 pi. Yes, 0 to 2 pi. So we're going to use this formula, right? So we're going to use this formula. Then now we just need to put down the corresponding data. Data go from 0 to 2 pi. And use this formula. The outer curve is this one. The inner curve is this one. Now this one here, you use the perfect square formula to expand this. Expanding this, we use the perfect square formula to expand that, right? And notice that again, you come up with this cosine square data again. So again, you use a half angle formula. So you use it again and again in when we do integral of polar curve, okay? Polar equations. Okay. And then for this one over here, looks like you have a square of sine 2 data. So we're going to use half angle formula again. And what do you think I should put here? What's the square of this? What does it equal to? That is what? So if it's a square of this, then you go down 1 degree, right? So we'll go down, so it will become cosine of, now, and then you double the angle. So you reduce this exponent, but you double this angle. So double this angle, then you will get 4 data. Okay. But then the double angle formula say this is 1/2, 1 plus this. Okay. So notice that this one over here is double this angle. So when you reduce this exponent here, you actually double this angle here. So that would be this. Oh, hold on. It's not plus. This is not cosine. It is what? It's minus. Okay. So it is minus 1 minus cosine. Okay. So sine here will have a minus sign. If it's a cosine here, that has a plus sign. So this is sine. Then the double angle formula here will be a minus. Okay. Okay. Now after this, you can simplify this. Simplify. Okay. And combine lighting, etc. Then you should try to find the antiderivative. Okay. For antiderivative each one of this. Okay. And calculating, then you come up the answer here to be 20 pi. So again, I put down the double angle formula here to remind you, and you're going to use it again and again. Okay, here's it. So that's the end.